you definitely would be storing values. And you know what, that's going to be one of the huge functionalities on the calculator for us to make sure that we're utilizing whenever we think we can use it, that you are using that, because we don't want to round intermediate step values along the way. So meaning that if you find, like today, we're going to have to store a constant value for exponential models, and we want to use that same constant model or constant in our model every single time we answer a question related to that, especially in a free response or the next chapter when we're finding intersection points of two curves, and we want to store those values as unrounded and use it in a later calculation for another part of the free response, it's going to be essential that we store values and not just use the rounded values along the way, because it will throw off our final answer if that's the case. So we're going to start with exponential growth and decay, and I'll talk to you guys with like this is really, I would say 90%, well, no, 100%, no, 90% of it is a review from Algebra 2 Trig and Pre-Calc Honors. I saved the 10% for just what I'm about to show you, how to come up with the model. But when you're looking at a multiple choice or free response, basically an AP question, you're going to look for this keyword or phrase here, rate proportional to the amount of substance present. So consider a model in which the rate of change is proportional to the amount of substance present. So what that means is they're talking about a rate of change. So let's say you guys had the rate of change of a population or of the amount of bacteria, the amount of a substance, so dy, and then always with respect to time. So let's say they either give you this within the initial problem itself, or they'll tell you dy dt equals k times y is your model. Technically, in the problems that I've seen before, they don't expect you guys to do this process of solving for it every single time. They understand that you've seen it before, and then you can use the model thereafter. And the model should look familiar to you guys. It's one that you've seen in Pre-Calc Honors and in Algebra 2 Trig. So let's say you guys were given this. Your variables are usually y and x, but in this case, they're y and t. So what we're going to do is separate the variables, y on the left, t on the right. So t is like your x, just kind of think of it like that. So in multiplying both sides by dt, we get dy equals k times y times dt. K is just a constant, so I'm going to go ahead and leave it on the right-hand side, but y I'm going to move over to the other side through division. And so I end up with 1 over y dy equals k times dt. At this point, once the variables have been separated, if I'm trying to solve, and right now what I was given was a differential equation, a rate of change, which is a derivative, and what I'm trying to do is come up with what the solution is, which is what y is equal to. So you guys know at this point that you would integrate both sides. So we get ln of the absolute value of y is equal to, if k is a constant, then it's just k times t plus c. Okay, so you guys have done a few of these, I think, on the homework assignment now. So where we now have to exponentiate both sides to get rid of the ln. And then in doing so, you guys have absolute value of y is equal to the e to the kt power. And then remember, when you're separating by addition, I've seen this mistake a couple times already on the homework. The plus sign indicates in the exponent that you guys can separate these two to be the multiplication or the product of e to the kt times e to the c. Now we, in exponential growth and decay especially, when you guys look at your model, they replace the e to the c, which is 2.71 to whatever that constant is, with a different value called a. And so if we do that, that a represents something when you guys learned it in Algebra 2 Trig and Pre-Calc Honors. Does anyone remember what a represented in growth and decay models? What did the a represent? Anyone recall from your previous classes? It had a significance in the problem. Nobody remembers? What if you guys plugged in 0 for time? Yes, principal amounts is what I heard someone say. And then the starting amount, perfect, yeah. So if you guys plug t equals 0 in, you would get e to the 0, which is 1. And therefore, at time t equals 0, your initial starting amount of whatever it is, the population of something, the amount of a substance, or the amount of the number of bacteria is A. Okay, so usually this is going to be your initial amount. And let's go ahead and put, when we drop the absolute value, we technically get a plus or minus that you can or cannot, if you want to, absorb it into the A value. I think Heather was the one that on her homework assignment, she's like, okay, I get it now, but I think it's still kind of weird that it just kind of like gets absorbed into it. So now when you guys look at your problems and you're solving the problems, it'll become more clear as you guys solve more of these questions why it doesn't really matter. So whether or not you define it as positive or negative, with the A or not is going to be really ultimately clear that we all get to the same answer because of the conditions that they provide, like that the fact that they give you guys certain parameters, like in example 1, that it has to start with this amount. So it's not going to matter in the end. So it's important that we just as we're doing these problems, understand that for someone who redefines something as K as having to be positive, representing growth, and then someone defining K as negative, that it really doesn't matter in the end, because if I ask both of you to write down what the model is, our models would look exactly the same with the specifications that are provided as initial conditions later on in these problems. So that's going to be the model. So I would say that if you guys within a problem, if they start off by saying this relationship here, that the population is proportional, the rate of change is proportional to the population, then you guys can automatically jump from that to that. You don't have to solve that model each time, because that's kind of like a proof of how do we get to that model itself. Okay, so here you guys have a bacteria culture starts with 200 bacteria and doubles in 1 hour. How long does it take to reach 2,000 bacteria? So I'm just going to kind of give you guys some refresher. These problems should look familiar to you. You've seen this level of problems before. So usually with these, they're going to ask you guys, give you guys certain parameters so that you can solve for your two constants. You're going to be able to solve for A and for K in your model. And ideally with every model, you guys have just two variables at the end. Y, which is your amount or your population size, and then T, which is time. So in this case, I'm going to bring down the model that I said is okay for us to use now. Okay, so that's going to be the model we begin with. A bacteria starts with 200 bacteria, so automatically they give me the initial amount, so 200. And then I look to see what else is given so that I can solve for K. So they do tell me it doubles in an hour. So what is Y if the population doubles in an hour, if the culture doubles in an hour? What is your Y value? Yes, okay, it would be 2 times Y, which should be 2 times 200, which would get you guys 400, right? So 200. E to the, and it doubles in an hour, so time is 1. Okay, so here you guys have that you're going to isolate K by dividing both sides. We can't ln something unless you guys have cleared the constant in front of E. Once you guys do that, then at that point you guys can ln both sides. So ln of both sides would then get you guys K is equal to ln of 2. At this point, can you guys practice the whole storing? Can you store ln of 2 into A on your calculator? So hit on, and then you guys are going to store. So let A equals ln of 2. And so when I write my model, I'm going to give you guys just a minute. And then if you guys can type into the chat, when you feel like you've stored the value in A, you've double checked that that value is indeed A. Can you just type in yes, you're there already? Just yes, or if you don't understand it, tell me no, so that I can go over that process again. Okay, so everyone should have ln of 2 stored in for A. And also, if you guys can write that into your notes as well, where you say let A equal ln of 2, or let's say you decide you wanted it in X, or sorry, not bad variable to pick, but let's say you wanted to store it in C, you could call it let C equal ln of 2. And then at that point, when you write your model out, so my final model for this one would be y equals ln of E and then A times T. So long as the reader somewhere in, yeah, it's supposed to be stored as a decimal, and on the calculator, it's unrounded. So on here, when I'm the AP reader, I would know, okay, so she defined A to be ln of 2. She then used A later on, and that's helpful to know because especially when A gets more complicated or your stored value gets more complicated, it's just faster if I can just define a variable and use that variable through my calculations. All right, so here after this, now the question, you're going to answer the actual question. And the question says, how long does it take to reach 2000 bacteria? So how long does it take indicates that you guys are solving for time. Can you guys go ahead and solve this equation first on here showing your work? Can you guys go ahead and solve this for time? And your answers are going to be rounded to 3 decimal places. Go ahead and round it to 3 decimal places. Yeah, I'm sorry. Heather asked a great question. Like in my head, as I was telling you guys to do that, here where A is equal to ln of 2, is that A different from this A here? I apologize. Yes, it is. It just happened to be the first letter in my alphabet on the calculator. So I always just store everything in A, which is probably not a great idea to do when I'm introducing this to you guys. But yes, this A amount is the initial amount, and this A is defined as the constant. So I apologize about that. We could, that's why later on I said, oh, maybe you guys can store it as C or as K. So you can store it, you can call this variable whatever you like, and then just make sure that it corresponds to this right here. Thank you for pointing that out. And go ahead and type your answer into the chat if you guys have an answer. Oh, yes. Thank you, Min. It should be T equals. Okay, so T equals 3.3. And then you guys, when you're rounding in calculus on a free response multiple choice, they're always provided out to 3 decimal places. So again, try to get into the habit of doing that. It will be marked incorrect on the AP test if it's not exact to 3 decimal places. And that's why it's so essential that we store values along the way. So 3.322 hours, and always tie the units to it. Okay, the other one that you guys learned before, I think someone had, when I asked what does A represent? Someone said that it represented the principal amount. So when we're dealing with compound interest, and we have, when a child was born, her grandparents put $1,000 in a savings account at 10% interest, compounded continuously. What do you guys remember what the model was, which is really essentially the same thing as AE to the KT, but they just changed some of the variable assignments and called it something else, or really the constant amounts. Yeah, P equals A. Do you guys remember that? And what did they call K in these interest type problems? Yes. So you guys will remember PERT from previous years. So P is really your A, your initial principal amount is your starting amount. And then R is your interest rate, which you always write as in a decimal value. So in this case, we know what A is equal to. It's 1,000. And then the interest is growing at 0.10. And they want to know if the child, and it's compounded continuously since she was born. So if the child takes cash out at age 20, how much is in the account? So super easy question. I just wanted to make sure you guys remembered. These models are all the same thing, whether it's exponential growth, decay, or if you're talking about compounding interest. So go ahead and type into the chat, what do you guys get when you enter that in? Good. And it's just the problem above that I had said round to 3 decimal places. Then this one I'm going to say make sure it makes sense with whatever it is that is representative of it. So if you guys put it out to 3 decimal places, that's fine. But I would say only for these types of problems would it make sense for you guys to be okay to round out to 2 decimal places because it does represent cents. So 7,389.06 dollars would be the amount. Someone typed something else in, so I'm not sure how. Oh, just make sure that this is in the exponent. You might not have had that in the exponent. Can you just double check that again, and then just make sure that you get that right? And also when you guys are using E, I'm not sure if you guys are using the one above ln or not, but E is the one that's above ln, and then the rest of that should go into the exponent. And that might have been where your error was, if you guys made a mistake on that. Okay, perfect. Okay, so half-life we see through. Do you guys do that in chemistry? And do you guys remember doing that in chemistry? Bio. Okay. Yeah. So in I remember the AP Chem teacher at Edison. The first time she taught AP Chem, she came to me and she asked me like, what's going on with all this log stuff? And so I remember that what you guys learned in science looks slightly different from what you guys learn here, but you can apply the same concept. It's just that you can solve the questions. I feel like in science, you're just given the formula, you just plug it in. In this one, we have a starting formula that's the same as what we do with exponential growth. It's not any different than that. It just works out that your K value, when you guys are looking at something that is half-life, that it is decaying rather than growth. So you see an exponential function that's decreasing rather than increasing. But it's the same exact model. That's why I kind of like that when we do it, it's just like it's the same exact formula as opposed to, oh, half-life is a different formula. So if carbon-14 has a half-life of 5,730 years, that means after that amount of years, whatever amount you had to begin with would decay down to half of the amount that it began with. How old is an item with 60% of its carbon left? Okay, so for sure we have to solve for what K is equal to. You'll notice that when you read this problem, it doesn't give you guys a starting amount. So I'm not going to even bother building a model for this, but I'm going to use what I know about half-life to then solve for the value of K. So we're going to say solve for K first. Okay, so here is the premise of a half-life problem. If you don't have the initial amount, just assign a random initial amount. And what we will find is that each time we do this, it's going to end up with the same factor. Okay, so let's say imagine that you guys had 100. You don't have to write this out yet. If you began with 100, how much would you guys have left after 5,730 years? How much would you guys have left? You began with 100. Okay, you would have 50 for 5,730 years. It's half of the amount that you would have left, so 50 left. And then what if you guys began with 200? How much would you guys have left? And you don't have to write this out yet. 100. If you begin with 1, what would you guys have left? 0.5. And so I usually just start with 1 and 0.5 because what's going to happen is when you solve for the equation and you have like e to the kt over here, and you have to divide over anyways. 50 divided by 100 is a half. 100 divided by 200 is a half. So it doesn't really matter in terms of answering this question what you begin with. So start with whatever makes sense, but the idea with half-life, I'm just going to put 1.5, is that it gets reduced down to half the amount that you began with. And then that way we can solve for what K is, because after 5,730 years, you should have half the amount that you began with. And so in solving this, this is where why you guys are given a formula in bio, because each time you guys do this, I'm sorry, I'm probably skipping this one step, but you're taking ln of both sides at this point because you already have 1 in front of e. And so when you do that, you have the ln and e undo each other. So you have 5,730 times k. And so each time you do this, you should have ln of 1/2 divided by time as your constant. Okay, so on your calculator, and just because this is respecting what Heather had pointed out, we're going to say let C or let K be equal to, let's just keep it consistent and call it K. Let K be equal to ln of 1/2 over 5,730. Okay, why don't you guys practice doing that? Store it actually in the variable K. Go ahead and store that in the variable K. And just double check again that it's actually stored as K. You should get some really small decimal amounts for that. And I also like to say let, just so that the reader knows, I did actually check for or solve for K, and that I'm defining K to be that. Okay, so for this particular problem, it didn't ask me to write the model out, which a lot of times it does, but it didn't ask that because it didn't give me a starting amount. So what we can do after that is go on to answering the question. Since we don't have an actual model with an initial amount, the question is, how old is an item when 60% of the carbon is left? So we're going to use the same constant value, and this time, if you start with 1, how much of 1 is still left of carbon 14? If you guys start off with 1, this question is asking for how long it takes for it to reduce to 60% of what you guys began with. So 60% of 1 should be good, 0.6. So half-life is 1 and 0.5. So anything else after that, if they say 60%, that's reduced down to 0.6. And then we have E, K is what we defined earlier, and then time. So at this point, we can take ln of both sides if we're trying to solve for time. And we get ln of 0.6 equals K times T, because ln will undo E, divide by the K amount. And can you guys tell me what time you guys get? Use the stored value for K. Use what you guys stored for K. Okay, perfect, you guys. 4,220.813 years. Okay, just looking at the time, I have about 10 minutes to start this. I did have it in my plans to continue this on Friday, but those were more like refresher questions, just things that you have seen in the past, and trying to tie it in with what you're going to do on the AP test. I would say exponential growth and decay. It's one section again of the chapter, and it's in terms of like importance on the AP test. You don't see whole free responses dedicated to it anymore. Maybe a part of a question, but I find that they stick this in multiple choice occasionally. And when they do stick it into the multiple choice, the many questions I've seen on exponential growth and decay is like this 1987 one where it says at any time t is greater than or equal to 0 in days, the rate of growth of a population is given by dy dt equals k times y. So once again, it's banking on you guys understanding that this is, when I see that, I should know this is exponential growth and decay, where k is the constant and y is the number of bacteria present. The initial population, which we now know is 1,000, and the population triples during the first 5 days. So write an expression for y for any time t is greater than or equal to 0. So for this one, you guys can just, notice it doesn't say solve the separable differential equation of dy dt equals k. It doesn't say solve this. So I'm not showing all the steps in between. I can just go into recognizing that this is growth and decay and using the model itself. Okay, so we have A is equal to 1,000. So for now, we know Y equals 1,000 e to the kt. Anytime they ask you guys to write an expression for the model, another way of thinking about that is solve for k. So right now you want y as a function of t. So I'm going to quietly do that. Can you guys go ahead and use the information of the population tripling to solve for k? Can I have you guys also work on storing that k value in a variable, in the variable k? Okay, can you guys type into chat, yes, you guys got that answer? No, if you guys didn't get that answer, let me know. Okay, so the next thing I'm going to talk to you guys about, and we will definitely hone in on this skill. It's not really a skill, but it's just, you guys know this. In math, sometimes they throw you a curveball, and AP tests, of course, they're going to do that. They'll ask you a question that you don't anticipate or you've not seen in that context. And so by instinct, actually, in fact, someone had quoted that in the last test correction. Instinct is what you use to just, okay, I'm not too sure what the question is asking for, but I'm just going to go with what I can do with this problem. And maybe it's going to lead me to a light bulb coming up about what to do after that. So maybe when I'm reading part B and it says by what factor will the population have increased in the first 10 days, I'm not entirely too sure what the question is asking for, but I know that I can take a stab at it by figuring out, okay, well, what is the population after 10 days? So can I have you guys use your instinct and solve for that? What is the population going to be after 10 days? Then go back and reread the question and see if you guys can come up with an answer for this. And then type it into the chat. If you think you understand after getting the answer what the question is asking for, what do you think the answer is? The final answer. Yes, for the few people who have typed it in so far, that is correct. Okay, so initially, let's say you guys got, you weren't sure what to do, except for you knew how to answer the question after 10 days. I know the population is 9,000, but it is asking by what factor will the population have grown? So if it started off with 1,000 and now it's 9,000, a factor is something through multiplication, right? So the factor would be, for those of you guys who typed it in, that is correct. 9 is the factor. It grew by a factor of 9. 1,000 times 9 is 9,000. Yeah, that is conveniently nice to get that. So now part C, at what time t in days will the population have increased by a factor of 6? So go ahead and solve for that next. Again, now we know, okay, by a factor of 6 means 6,000. Okay, perfect. 8.155 days. The other class I was able to get up, and you guys we're going to end in 3 minutes, but I'm going to have you guys just wrap up with A for the next question. The next question is going to give you guys oils being pumped continuously from a certain oil well at a rate proportional to the amount of oil left. So again, here, rate proportional. They give you guys this differential equation. And then they say initially there was 1 million gallons of oil in the well, and 6 years later, there's 500,000 left. So kind of like almost a decay problem. It will no longer be profitable to pump oil when there's fewer than 50,000 gallons remaining. So for A, they just simply want you guys to write a model for that. So we're going to go ahead and plug in after 6 years, the million gets reduced down to 500,000, e to the k times 6. Okay, go ahead and solve for that and figure out what you guys have left, because 1 million down to 500,000 is like our half-life problems. Okay, you guys, you can see the answer here, but can you guys type into the chat? Do you feel like most of this has been reviewed for you? Yes or no, or how was the lesson for you guys? It felt like you guys have seen it before. And I feel like the exponential growth and decay problems are not anything new, except for the fact that they just throw that dy dt at you guys, and the proportional, this part of it, you guys have not seen before. So, obviously we didn't do the lesson, you'd be like, okay, what does that mean? But the rest of it is review to you guys. And then after that, parts of it are going to be calculus related, but back to old chapters. So starting with question B, that's going to be a review question. And then this one in particular, they start bringing other concepts into it. You guys look at the years. It's really old. 1987, 89, and then 96. And as we progress through the free responses, as we go through the years, what we find is that the free responses tend to, you'll notice that the first two were all strictly based off of exponential growth and decay. Exponential growth and decay here, with maybe B being a little bit of calculus. But then in 1996, even before I took the test, it was already starting to see that only part of the question is exponential, and then the rest of it is like they tie in other concepts from previous chapters. So we'll get to that one in class the next time I see you guys. Otherwise, if I don't see you at tutorial, I'll see you guys on Friday.